Mark, please, maps and data.
Thank you, Hannah. Is this on? Can everyone hear me? Yes. Sorry about the technical delays there. Always happens, right? Thanks for coming to this talk. In essence, all that I want to do is convey a very simple message, which is that very often people have a map, they have some spatial data, they want to overlay it, and they have to ask themselves a difficult question of how I combine my data with a map. They think about a map, and they think about adding data to it. It's a tricky question to answer. And the sole point of this talk is to say that maps are data, and hopefully convince you that there's a better way to do it by using the underlying map data themselves, rather than answering the difficult question of how to put your data on a map. My screen of gratitude for the support for this work comes particularly from the Austrian Science Foundation, who funded this research, as well as the other institutions mentioned there. This map was produced entirely in R. As an example, this is a data map. I will shortly get to how such maps can be constructed. The packages to do it are called, first of all, OSM data. So OSM here is OpenStreetMap. OSM data brings OpenStreetMap data into R, and the package OSM plotter then enables you to plot the OpenStreetMap data. Before I get on to the how that's done, I'll address the very important question of why. Why is there a need to do this? To motivate this question, I'll quickly show two sample maps. These are from an event that's held every year called the Esri Global Users Conference. Esri is this company that makes a piece of software, commercial piece of software called ArcGIS, that most of the kind of non-R world use to make maps. And this was from last year. This was the first prize map in the professional category. And you can see here, it illustrates the difficulties of asking the question of how to combine your data with a map. This map data thing has bits where there's no data and the map comes out. Then there's bits, obviously, where there is data and the map disappears behind it. And then the data themselves are all pixelated for presumably no particular reason at all. And obviously the question of exactly how best to combine the data with the map is really quite difficult, yet there's still won first prize. A second example is this map, which purports to indicate walkability. Again, the person's obviously gone to a great deal of effort to answer the question, how can I best combine the data with the map? It's about walkability. I think that when I walk, I usually walk along a street, but this map seems to show me that walkability happens in the blocks between the street and not on the street. And little aesthetic things like this, we simply train ourselves to overlook. And part of my argument is the world shouldn't be that way. We shouldn't have got to the stage where we train ourselves not to question this map and go, hang on, the streets aren't walkable there, just the bits in between the streets. That's a kind of a strange concept. Very difficult question to answer, how best to combine maps with data. Right, back to the basics. Here's a map. First pop question for the talk. Does anyone know where this is? This is a map of this area of Brussels, and that's where we are, in that building there. And this map itself contains a lot of data. So if I've got some data and I want to overlay them on the map, to come to the whole point of the talk, instead of working out how best to do it in circles or squares or dots or whatever patterns that I can print over top of this map, why not simply use the data of the map to plot a visual surface, a data surface on the map with a corresponding scale? This is like the big woo moment of the whole talk. This is the point of everything, that you can make maps with in this case, a data surface using the underlying map data. Here I've used the buildings, which again, if this was walkability, wouldn't be appropriate. Instead of using the buildings, I might like to use, that's that map again for contrast. So that's the winning map of this massive global thing, and I do think aesthetically, this map has a little more to offer. Still use the buildings. For walkability, for example, you might want to use the roads, and you get a map like that. You can use any elements whatsoever within the map to highlight things. This is buildings and roads combined. There's also a lot of train lines around here. You might want to look at walkability along a train line, for example, and use any color scheme you want and get a map like that. So anything is possible. Right, that's the motivation for it. Now, very quickly, to go through I just realized that I don't have a timer here on account of changing computers, so can you? Thank you. That should be fine. Very quickly go through these 3 points. The first one about OpenStreetMap data, the second one about how to make maps, and then mostly about how to combine your data with maps. I will presume people are vaguely familiar with OpenStreetMap data, but not particularly familiar. So a very quick introduction to OpenStreetMap data. Second pop question of the talk, What's the least mapped country on the planet? North Korea. Right, North Korea. Let's go to North Korea for a tour. Now, if you look at a map of North Korea, I didn't want to choose Pyongyang for this because I know that Pyongyang is actually a little bit mapped. There's a main highway that goes to the north of Pyongyang. There's only one. That highway hits a junction at the first major city outside of Pyongyang. It's about 200 kilometers north of it. The city is called Anju. If you look at Bing Maps and look at Anju, this is what you get. The colors are a little bit hard to see perhaps, but there's a crossroads there. No matter how far you zoom in, you get nothing more than a crossroads. If you go to Google Maps, you get a little more detail. Again, sorry about the light color scheme, blame Google for that. There are a few roads here, there's a train station, there's a strange restaurant, and that's about it for Google. And this river does this weird cutoff thing. If you look at the corresponding satellite image, you can see that there is a whole city there, there's a river there, it has a whole lot of side branches, it has a whole lot of structure, both to the city and the river and the streets and everything, and yet Google gives you that, nothing there. OpenStreetMap gives you that. The river in all of its glory, all of its side branches, most of the buildings in the city. That's my political statement. I wrote the package OSM data, obviously passionate about OpenStreetMap. OpenStreetMap is really, really good and quite often will give you things that Google can't give you, that Bing can't give you. Right, the end of the political statement. So the package OSM data uses a server that's called the Overpass server. It's just an online server that delivers OpenStreetMap data. So to start getting the data in, use this function called OPQ, which is an overpass query. Don't worry about the reasons why, it's just called OPQ. And is that easy to read for people? Not particularly. Anyway, you can just type OPQ, Anju, North Korea, and it will give you back this formatted bunch of strings that are then mashed together for a URL query to give you the data. You can then feed that into a function called add feature. In this case, that says buildings. I want to find all buildings in Anju, North Korea. It modifies the query slightly by adding a feature called building, and then finally to a function to extract the data. This OSM data package can extract data as simple features, SF format, or as plain R spatial format, SP, and has effectively two primary functions. One is OSM data SF for simple features, and OSM data SP. And when you do that, you get this object back which contains every single aspect of the OpenStreetMap data that pertains to buildings in Anju, North Korea. And there's on the list there, you can sort of see what some of them are. The thing itself contains, the actual data are in the final five. It contains a list of points and lines and polygons and other things like that. So we can store that in an object, name it dat_b, and look at how many polygons are in there. So this is how many buildings OpenStreetMap has in Anju, North Korea. There are 565 of them. Remember, Google Maps has one. Highways do the same thing. Just type in key equals highway instead of building. In OpenStreetMap, all roads and footpaths and horseways and things like that are all called highway. That's the generic category for it. And there are 412 roads. Bing Maps has 2. Google has about 5. So you do get an awful lot of data. And these colors that are a bit hard to see, these things in simple features format are data frames. So you can simply look at the names of the rows of the data frames. And you can see, for those who can barely read it, up the top there in the polygons, which remember are the buildings, one of the names of the rows is tourism. And I saw that and I thought, wow, tourism in a weird out-of-the-way place in North Korea. And what you can do is then have a look at what values are given for tourism, and you discover that there's one building that's a museum and one building that's a viewpoint. So if you take away nothing else from this talk, you've just learnt something about North Korea that I'm pretty sure nobody would have known before. There is a tourism industry. Right, so that's all it takes to get the data out from OpenStreetMap and into R using OSM data. Just a few lines of code. You can also, this is OSM data functionality. The OSM plotter package that makes the maps has also a convenience function that does all of it in sort of one line. So that second box with explicit package names and ... thing, extract OSM objects just does the kind of second 2 lines of the box above in one simple line. So that's an option to use as well. Then how to make a map is similarly easy. This is the last time that I'll use explicit package names here before I go to OSM plotter, but you can get the bounding box for a place using OSM data. And then in OSM plotter, call a base map, which just defines the proportions of the map and the scale, the limits of it, and then add OSM objects. So here you just make a base map, you add highways, and you add buildings, and you've got a map. And then finally, there's an internal print function. These maps that get made are ggplot objects, but the internal print function ensures that when they're printed, the object that comes out has the exact proportions of the bounding box. If you use ggplot, you just get a default proportioned object, or you have to work it out yourself. So this just automatically prints a map. So if your bounding box is really long and skinny, your resulting map will be really long and skinny. Right, this is the result from Anju, North Korea. Quite often, if you type in bounding boxes, it gives a relatively large area. Anju, North Korea is defined as a quite large region, much more than just the inner city. So you can manually zoom in on the bounding box and get a map there. To reiterate again, that you cannot get from Google, you cannot get from Microsoft. Only OpenStreetMap gives that to you, and now this package in R enables you to make maps in R in 4 lines of code that you can't do any other way, which is kind of cool. Right, back to here. More complicated examples. This is the bounding box that I arbitrarily picked around where we are, and the wild gallery highlighted in the yellow and the red there, and quickly step through how this was made. Simply download the data. It's very, very simple. Download the buildings first, download the highways, download the railways, because there are a lot of them around here, download parks, and sometimes things are a little bit tricky and require keys and values. There are helper functions in all of these packages that explain this and that help you find out what keys and values to use. So in this case, the water, the canal over on the top left has a key of natural and a value of water, and that gives you the canal. So you get all those objects. You then define some colors for your maps. There are a lot of default color schemes in the OSM plotter package. That map's made with one of them where you don't have to define colors, but you can define them any way you want. It also has a function called adjust colors, which takes any color, vector, single value, whatever, and adjusts it. In this case, makes the colors 20% darker. And this is quite useful for plotting, for example, buildings and highways in the same color scheme, but you want the highways still to contrast against them, so you can darken or lighten them by some relative proportion. So that's effectively all that's involved in the preparation of a map, is to get the data and then to define a color scheme. Once you've done that, you make the map. Again, you start off with a base map. You simply add all of the objects, and there's also a function at the end, add axes, which just automatically adds axes. You can specify a whole lot of parameters for how they look and where they're placed and stuff like that, and then print the map at the end, and that's the result that you get. So that whole map took this much code to download it. Most of that was specifying exactly how to get the building outline here. So the more specific you want to be, getting that polygon for this building is quite specific, and you have to sort of work out what to do, but the generic data is really easy. And then 12 lines of code, and you've got the map. So that's how to make maps. And now I should have just a few minutes left to quickly go to data maps. Right, same process. You start with a base map, you add objects. I'll step through it here and go through the building of a map. This adds the waterways, defined by colors, and there's a border argument that says I want to have a contrasting border, and that's got to be in a different color. The size argument will be interpreted according to what the object is. For a polygon, size can only be the border, so it's the border. For a line, size is the width of the line. For a point, it's the size of the point. Then add parks. No border argument here. The park doesn't get a border. The colors defined like that. Add the railways. And that's probably about enough for the base with the axes, and then adding data. All we do then, instead of the add OSM objects argument, we get some data first of all, pretend there's some function called get surface data. I've gone and done some experiment for months that's been funded by a scientific agency and collected a massive data, and they can be any form at all, but at the end result you feed in coordinates and values. They can be gridded, these ones are gridded, they can be just randomly placed points, it doesn't matter, and you can control how they're interpolated in terms of the surface that's fitted on the map. You define colors for the data, one of the color brewer palettes here, and then instead of add OSM objects, add OSM surface, and you plot the surface of the data. So that's the buildings highlighted with this simple matrix of X, Y, Z data. You then add the color bar with another very simple line of code, and that's the resultant map that you get. So that whole map was made in 12 lines of code after having downloaded and prepared the data. What you'll notice is that here, because I've stepped through the way that I illustrated it as it got built up, the axes got added on the 4th line, then the surface got added, then the color bar got added, and then the highways got added over the color bar. So if you look at the color bar on the side, there's highways on top of it, and if you look at the axis down the bottom, it's got also buildings and highways over the top of it. So the order of plotting matters. Things will be plotted, things will be overlaid sequentially according to the order you specify. That's like one of the most difficult issues of the package. I mean, it's a very, very simple way to produce data surface maps. You can also do categorical data. I should now have about 2 minutes left. 1 minute? Right, categorical data. That's continuous data. For categorical data, we're talking clusters. We're talking here's a group defined by this, here's a group defined by this, and they're all spatially defined. There's also an equivalent function. Instead of add OSM surface, add OSM groups. Functions exactly the same way. You can specify the colors. Here I've got 12 groups and fed in a random 12 rainbow colors, and the result's pretty horrible. And there's one last function that is called a color matrix that enables you to generate aesthetically far more pleasing colors. This is the equivalent of any color palette, but it does it in 2 dimensions. You feed in the 4 corners from Color Brew or whatever palette you like, and it will do a 2-dimensional interpolation of the color field, which you can also rotate around to get nice looking categorical maps as well as continuous maps. The end. My final expression of gratitude to Bob Rudis, Robin Lovelace, and Mayor Salmon for helping write OSM data, which is most of the programming effort for this. And these packages are hosted through rOpenSci. They're on GitHub. Please contribute. They're also both on CRAN, so start using straight away. Thank you.